Before we look at how do we change the representations for a linear function when we change bases, you need to recall what is the representation of a linear function. So what we know is this diagram and these two equations. So we have a linear function f between the vector space v and w. For v we choose the basis b tilde and for w c tilde. That allow us to introduce column vectors in Rn and Rm depending on the dimension of v and w. And we saw in previous lecture that if v connects a particular element between this space and that space, then the corresponding x and y are connected by the matrix A. So A represents f with respect to these two bases. In fact, we can even write it like this. So A is the matrix of the linear function f with respect to b tilde and c tilde. This is a new notation, but I think if I just use A, it's just easier. And you need to remember A works like this in the diagram. Now, connected with that diagram, we derived in previous lecture the following equations. So f of b, so the image of b, is c. So when f acts on the basis elements, it gives me some element on w, but since an element of w can be written in terms of c, well, it can be written as c tilde times a. That's it. How f acts on the basis is what it means, this equation. So we have a matrix A. Now, if I know how f acts on the basis elements, I know how it acts on any vector of v. In particular, if you have v belonging to the vector space v, f of that, well, is written like this, is c tilde a times x. When x, remember, need to remember from previous lecture, is the representation of v with respect to b. So we have the problem to solve. To compute this x and then do this calculation. Now, this is what we know. If I want to change bases. I want to change bases on the domain and codomain. And to do that, I'm going to introduce new functions, bijective functions, or meaning invertible functions. The function p goes from v to v and q from w to w. If I have those, I can do what we have seen previously. I can define a new basis. I can define a new basis for v, b prime, which is p times all bases, meaning b tilde times p. And I can define a new basis for w, c tilde prime, which is q times the original basis, so c tilde times q. I can get the matrices p and q directly from the mathematical expressions of p and q. Right now, these are not important. Let's just assume that we have them. If we have them, we can easily compute p and q, the matrices. And moreover, they are invertible. Like p minus 1 exists and q minus 1 also exists. If I have these new bases and these new bases, now I can switch between old representations of vectors and new representations, like this. This is what we've just seen. The thing is this. I have a function between two vector spaces. For the domain, I have two basis functions. For the codomain, I have other two basis vectors. The connection between basis vectors is established by p and q, here, like so. Well, I can represent my f here with respect to the original basis that I chose for the domain and codomain. That gives me a, and I can write this. Or instead, I can introduce into the domain b tilde prime and to the codomain c tilde prime here, and I have another matrix, A prime. So the question is, how is A prime connected with A? This is our goal, is to get that. So to do that, let's introduce what we know so far into this diagram here. What do we know? Well, we know that x prime, from x prime, big X prime, we can get x by multiplying it by p. This is that equation here. This is what we can do. We also know from this equation that from c I can obtain c tilde prime. So let's write it like this. From this, I can multiply it by q. On the diagram, what we have, well, from c we get c tilde, like this, like by multiplying by q. Similarly for b, b tilde gives us b tilde prime by multiplication by p. Additionally, we know how to express the connection between vector representations. So if I have an element, for example, of v and I represent it with respect to b tilde prime, so I get x prime, right? X prime, when multiplied by p, gives me x. So when v is represented with respect to b prime. So I have a connection between Rn and that Rn there. Can you see? By multiplication by p. Notice the order. From b multiplied by p gives me the b tilde prime. From x prime I multiply by p, I get x here. Similarly, the same thing happens here. If from c I multiply by q gets me c tilde prime, if I have a representation here y prime, to go to y, I multiply by q. Like so. So the order is reversed. Can you see? Very important idea. To see these equations in the diagram. Now, but still the connection remains to be done. How is A prime connected with A? Let's focus on this, what's written here first. Fv is written like that. This is equal to that, by the way. So let's try to rewrite this in such a way that c tilde prime shows up here and x prime shows as well. So let's do it. So c tilde is written like that. It's c tilde prime times q minus 1, right? We just rearrange this. Then the a stays there, and then the x. X is p times x prime. So it's p times x prime. Can you see the idea? Look at it. What's written here must be that. Can you see? Just compare the sides. Fv is Fv, so this is the same. So this thing must be that thing. But for that to happen, this is that. So A prime is q minus 1 AP. This is the connection that allows me to convert between the original matrix representation for our linear function and a new representation. This connection can be seen from the diagram. Look at it. If I have a column vector here, I can convert it to a new vector by multiplication by A. This is one path. Well, alternatively, I can start with that column vector, multiply it by P, multiply it by A, and then multiply it by Q, the inverse of Q. Can you see the idea? First P from here to here, then A, and finally, because Q maps from here to there, you want to the other way around, you multiply it by Q minus 1. That. This is the connection. It's already seen from the picture. The connection between the matrix representation of our linear function.